Hi everyone, in this video we will show what liquid-liquid extraction is and how it looks like. Sometimes the products in a process are to be obtained pure, but they are often mixed within the reaction products and the initial substances that didn't react. Therefore, to obtain the desired product, we need to add separation units to the process. One of those processes is the liquid-liquid extraction, which can be used when the desired compound is on a liquid mixture. It is necessary to add the feed that contains the mixture to a separation unit and add a second liquid as a solvent. Then mix it up and let the mixture at rest to obtain the solute away from the initial feed. The solvent that's to be used needs to meet these requirements: immiscible with the feed flow, high selectivity for the solute relative to the feed, high volatility difference relative to the solute, inert to the compounds in the mixture, and so on. Once the solvent is selected, we proceed to choose the equipment needed. Some of them are mixer settlers, spray columns, plate columns, and so on. And finally, when all those parameters are chosen, the process looks like this. The liquid containing the solute and the solvent enters the unit. Then they both mix up and the solute begins to transfer to the solvent. Once the equilibrium is reached, the fluids are left undisturbed, and after that they separate. The solvent which is rich in the solute is known as extract, and the carrier is known as raffinate. To know the quantity of solvent that's required, the raffinate and extract composition, and the system performance, it is necessary to visualize the process in a diagram. There are different types of diagrams, such as the ternary diagram and the rectangle diagram.
In the ternary diagram, we have an equilateral triangle. Each of its vertices corresponds to a substance: the carrier, the solute, and the solvent. The substance compositions are plotted as lines parallel to a vertex, meaning 100% at the vertex and a 0% at the bottom. The distribution of the components is described by the equilibrium curve, which describes the partition between the solvent and the carrier at any time of the process, meaning that at any time the solvent has this composition of solute, whereas the carrier has this composition, making a dome. The upper region is known as the miscible region, and below the curve is known as the immiscible region. Here is shown an example to illustrate better the usage of the method. The acetone concentration of a 3000 kilograms aqueous solution needs to be reduced from 40% weight to 2% weight or less, using at least 2000 kilograms of pure trichloroethene (TCE) in each stage, in a cross-flow operation with only one mixer decantation. So, how many stages are needed? What is the quantity of raffinate and its composition? First of all, we need to propose the material balance in the unit. Inputs equal to outputs, since no reaction is taking place, so feed plus solvent equal to raffinate plus extract. Also, as shown before, the feed and the solvent get mixed together, so feed plus solvent equal to mixture. The material balance can be made including the solute: feed times acetone fraction in the feed plus solvent times acetone fraction in the solvent equal to mixed rate times acetone fraction in the mixed rate. So we can find the acetone fraction in the mixed rate and plot it in the ternary diagram. Using the tie lines, we can find the composition of the raffinate and the extract. As the end point is in the middle of two tie lines, we need to plot a new one. Now we're left with a two equation systems. Solving the systems, we find that raffinate equal to 2000 and extract equal to 3000. As the composition of the raffinate hasn't reached the desired composition, a second stage needs to be used. This time, the raffinate from the first stage is the feed of the second stage. Finding the endpoint and repeating the steps till the acetone fraction in the raffinate is found, we have that x equal to 0.02. Thanks for watching.